Alright, hello, and thank you for coming to watch my YouTube video on fixed point solvers. So we're going to start off with the fixed point theorem, and we're going to go from there into the algorithm, look at what it means, and then a physical example, then we'll go to the code. And I'll also be posting this code after the video to my GitHub. So here we go. So the theorem is basically if you have some continuous function g on the interval AB, and we let some g of a, not be equal to, it needs to be greater than or equal to for this to work, greater than or equal to a, and we say that we have a g of b, and this guy is going to be less than or equal to b. Then we'll say there exists a fixed point call it x star on the closed interval. And briefly, it's kind of the idea of the algorithm is we're going to say that this only works if we can write it in the form that f of x equals 0 if and only if g of x equals x. Which means that we're going to try and write things in the form of g of x minus x equals 0. So that's already one area where your function might break down and not actually work. And then for the steps, we're just going to pick a starting point. So you pick your x naught, and then you say x of k plus 1 equals g of xk. And when you reach your termination criteria, you stop. So it's 3 steps, it's very simple, it's reliable. You just need to be able to identify if it's going to work for your function. We'll talk about that in a second. So to appeal to your logic on why this works, let's designate some other function, phi of x equal to g of x minus x, which is exactly what this is over here that we want to talk about. So during equality for a and b, we'll find that phi of a is equal to g of a minus a, which equals 0. And that means a is your fixed point, so we don't exist then. Similarly for b, then when you have the greater than or less than, that's when it's more important. So phi of a is going to be equal to g of a minus a, and we know that's bigger than 0. And we also know it's going to be less than 0. And then you can use your intermediate value theorem from calculus. And we can say therefore I should say equal 0, I should say x star. Yeah, we can write x star equals g of x star then. But basically, we get to conclude that there's a root on the interval, which is important to us. I'm not going to talk about proving when the root is unique versus not on the interval, and that's something you should be aware of. So if you have more than one root, you won't find them all when you use this solver. Alright, so if we want to look at an example though, let's consider f of x equals, let's do either minus x, because this is easy enough to look at. So what we can see here is that when f of x equals 0, then it's the case that e to the minus x equals 0, which means e to the minus x equals x if and only if f of x equals 0. So now we've picked g of x. And then what we'll do here is we'll kind of draw these two functions. Because if we were to graph e to the minus x by itself and positive x by itself, because remember, we write these in the form of g of x minus x, so this is just x as the function that we're looking at, then we can say that where they intersect is where f of x is going to equal 0. So let's graph that function. So this is y equals x, and then we'll say this is where 1 is, and we'll say that this guy is y equals e to the minus x. We'll go y1, y2 just so we know. It's not the same function. So then the issues that we can run into when we set these up is if we choose a value here on this side of the root, anywhere over here, what's going to happen is wherever you pick your function, we're going to look over here for y equals x, which we'll never find that. And then if you mess up a negative sign at any point in your derivations and you pick some point that is correct, you still will never get the right answer. It's worth being aware of that when you're troubleshooting if you mess up. I'll talk about another spot where I've messed up in the past and wasted time to try and help you out. Let's say we choose correctly, we set up correctly, what's going to happen? We're going to go this way. We're going to intersect him, then we're going to look for where we intersect. Again, and again, and again, and it's just going to keep this clockwise pattern going until it gets to our fixed point, or really until our termination criteria is met. And we'll talk about that when we make the script in Python. So let's go over to our program now. Alright, so now let's get going with this root finder. So the first thing that we're going to do is we're going to import numpy as np, because I like to use numpy. And then we're going to try and define our function. So we're going to define a, we'll call it fixed point, because that's the algorithm that we're going to be using for this method. And we're going to take some function g, initial gas, and tolerance. And then we'll, just in case we mess up, we'll go ahead and implement a counter. Max iterations. Yeah, that's a better one. Equals 100. Just in case they don't put it in, we'll go ahead and say at 100, we're doing it wrong if we don't find our answer. Alright, so we're going to need some xj to assign the new value to. It's going to be our x at k plus 1 basically, and then we're going to need a counter, and we're going to need a current error. So it's also good to put that in there. I'm going to say it equals tolerance plus 1. Okay, so now we're going to say while counter is less than max iterations and the current is less than tolerance. E current is no. Current's bigger than tolerance. Then we're going to say xj equals g of xi, and then we're going to set a new current error, figure out how much we're off by. So we're just going to look at the difference here of the new value minus the old value over the old value or current value. It needs to be over the current value to get a relative error. Perfect. So now we have a current error, and then we're going to say xi equals xj. Start over. And then when we're done, return xj and counter plus equals 1 somewhere in there to help ourselves out. So now the counter is going to tick up, so if we mess up, it'll try and help us out. So did we do this correctly? Let's find out. So we'll say g equals lambda for some x, minus x, and then common error is like you want to put the minus x here, your f of x. This won't work. You do not want that there. Remember, we explicitly are only putting the g of x in here because we're taking care of this every time we find our current error. See how I'm subtracting the xi? That's the subtracting of x. So don't want to put it out here, or else we'll break the system. Alright, so then let's just print our fixed point method of g, initial guess of, call it 1, tolerance. Sounds good to me. And yeah, we won't put a max iteration there. Let's see what we get. Perfect. So this is the correct answer given our tolerance. All right, thanks for watching. I hope this helps, and I'll post this on GitHub with at least with a try except in there for you. All right, have a good day.